Perhaps you have heard the Heisenberg Uncertainty Principle from your high school teachers before, but what does uncertainty principle means in the context of the quantum mechanics? Because literally uncertainty means something negative, like some error. Uncertainty is always associated with errors. Does that mean that whenever you use quantum mechanics, it is inevitable to encounter some uncertainties or certain degree of errors? No, actually it's not. So to understand what the Heisenberg uncertainty principle, we have to use both graphical and algebra description to explain what does it really means. Now, mathematically, the Heisenberg uncertainty principle can be written as delta x multiplied delta p large or equal to a positive constant. This positive constant is very small because h bar here represents the ratio of a Planck constant divided by 2 pi. And the Planck constant is a very small positive constant, 0.63 multiplied 10 to the power of negative 34 in the international system. Now in this formula, x is the coordinate of particle or the position, which is used to describe the position of the particle, where p is the momentum. Again, it is also used to describe the motion of the particle. In Newton's mechanics, both the position and the momentum must be well defined to describe the motion of the single particle. However, this is not the case in quantum mechanics. As, for example, if you want to measure the position or coordinate of the particle, you can use very good instrument, okay, and develop the very high experimental skills. And you probably will measure something like this. If you do this measurement several times, a lot of time, you will get something like this. You get this distribution of your data, of your measured results. I use very peak to represent these. Of course, there still have some, in the real experiment, some uncertainty is inevitable. However, I just draw this sharp peak to represent that in this case, your measurement of the position is very reliable because the standard deviation in this case, the delta x is very small, very small. So standard deviation is very small. And however, according to this algebraic equation, if the product must be large that is be positive constant, then the two factor cannot be zero at the same time. To be specific, that the smaller the delta x, the larger the delta p would be. So at this moment, if you want to measure the momentum of this particle at the same time, inevitably, you will get something like this. I use a purple color. See? That's purple color. This is a little bit exaggerate of your result, but that is a theoretical constraint. Okay? No matter how good your experimental equipment is, you still get this result. If you want to measure coordinate accurately, and the uncertainty in measuring the momentum increase. If you go to extreme, for example, if delta x is approach to 0, what would happen? And the delta p will approach to infinity. If I just use this equation to make this point. On the other hand, you might say, well, let's just measure the momentum first. Okay, forget about the position for time being. Yes, you can do so. In this case, we can use this sharp peak to represent that you can almost accurately measure the momentum of the moving particle. Okay, so in this case, the uncertainty is very small. However, if you say, well, why don't we measure the position or the coordinate of the particle at the same time, such as the position of electron near the proton, near the nuclei? Then inevitably theory will tell you that you will get something very uncertain when you try to work out, when you try to measure the momentum of that particular particle whose position, other way around. If the momentum is well accurately measured, then the uncertainty in measuring its position will get very large. Okay. Again, in the extreme case, if the uncertainty in measuring or standard deviation in measuring the momentum is small or actually zero, go to extreme, when delta p approach to zero and the delta x will approach to infinity. So that is what the Heisenberg Uncertainty Principle implies. But does this really matter? Does the simultaneous measurement of the coordinate and the momentum important? The answer is no. Okay. In quantum mechanics, we can either use the coordinate or momentum to describe the motion of particle. Okay. Actually, you don't have to use two variables to describe the motion of particle. Okay. Furthermore, it is forbidden to use these two quantum. It is forbidden to use both coordinate and the momentum to describe the motion of particle in quantum mechanics, such as electron near inside atom. Okay, how could that happen? Two reasons. Number one, in quantum mechanics, every quantity is described by matrices. For single one is a matrix. So that is how the Heisenberg's matrix mechanics was proposed first in the history of development of quantum mechanics. So both x and p, we use this one, are treated as operators. Okay, not just a simple variable, but the matrices. So both x and p belong to what we call the Hermit or Hermitian, if you use the adjective form, Hermitian matrices. So because they are matrices, therefore the algebra commutation axiom does not apply. For example, in algebra, A multiply B will equal to B multiply A. Okay, that is a basic algebraic axiom. We use it often. However, if you have studied matrices or linear algebra, you might have some expression. You have learned that if you put the two matrices in different order, and in many cases, they are not equal. They are not equal. X, we use this hat to represent its matrix. So in history, and Paul Dirac first discovered or actually revealed that the commutative relation between the coordinate and the momentum matrices must obey this what we call the bracket. Delta x and p. If you put into this is notation, this is called R. By the way, we have to talk about some what is negative in this case, negative, positive, negative, positive. So that is what the Dirac first shown that in quantum mechanics, this bracket originally called the Poisson bracket is called the Poisson bracket. In classical mechanics, of course, not in the Newton's original form, but in the Hamiltonian mechanics formalism. And in Poisson's Poisson bracket, this pronoun can be certainly written as that f and g, which are two functions of the coordinate and the momentum, can be written as and df, dx, and dg, dp, or per g, p minus and delta f delta p and delta g delta x. Okay, that is original form Poisson brackets in classical physics, in classical mechanics. But Paul Dirac realized that they still use this notation, this is form, but if you want to write it down here, so what does this Dirac bracket means is xp. Whenever you see this notation, which means that xp minus px, okay? In this case, both x and p are operator, not just a continuous variable with a single value, but in general must be written as a matrix form. So that is the Dirac's, so because of that, in the context of quantum mechanics, we have to use Paul Dirac's bracket. Okay. To cut the story short, if you go further, so whenever you encounter these called Hermitian matrices, of course, all the operators represent the physical quantity in quantum mechanics are Hermitian matrices. Okay, so they regard this one. So in this case, we just drop the conclusion. We will see that delta x, delta p is not delta p. Sorry, there is not or equal to this half, and this is can you see? We use a bracket. I use a Dirac bracket, x, p, and absolute value. So if you substitute this, I put the bracket, we use hat here, just represent the it is not just simply continuous variable, but actually that represent each operator in quantum mechanics must be written into a matrix form. So if we just apply Dirac's quantum, this is actually called a quantum condition. And this general condition, how to introduce Max Planck's constant. So this is a key relation. If you just substitute this equation into this mathematical property of any Hermitian matrix, then we will get this inequality. Okay, if you substitute that number, if you substitute this, if you substitute the right-hand side, I or by what is I, this represents the imaginary number. So if you have studied complex number, that would be the I represent square root -1. Okay, so if you substitute this one, if you substitute this equation into this one, then you will get this famous Heisenberg uncertainty principle. I hope this explanation will give you some new insight into this, what we call uncertainty principle. Uncertainty is not, there's no uncertainty when we use quantum mechanics. The only difference is that we can either use the coordinate or the momentum to describe the motion in quantum mechanics. Okay? And that is where we departure from classical mechanics. So in short, the coordinate and the momentum are independent. So if you want to measure them in classical mechanics, you can measure both of them at the same time. But because of this constraint in quantum mechanics, if h, the Planck constant, became important, then you have abandoned that scheme to use the two variables simultaneously to describe the motion of the particle. Okay. Thank you for watching.